Welcome to Module 6 from our series on constraint optimization. This module addresses duality, which was the topic of the last two modules, number 4 and number 5. However, this one specifically addresses how Lagrange duality may be applied to linear constraint optimization problems, also known as linear programming problems. So first, I wanted to draw a more clear distinction between linear and nonlinear constraint optimization problems. I think most of you watching this are familiar with the difference between the two. A linear constraint optimization problem is defined as shown below in terms of linear and affine functions. This is also known as a linear programming problem. We'll use the shorthand LP. However, this is not the standard form that's generally used for these types of problems. So one thing we're going to do in a couple slides is convert this shown here to this standard form. But before we do that, I did want to look at these equations and the components that compose them. So first we have our objective function, which generally is represented as the product of a coefficient array C, as well as the array of primal variables X. Our equality and inequality constraints, they both take a similar form. We have the product of a coefficient matrix A sub G or A sub H multiplied by the primal decision array X, and then we subtract out an array of constants, which are referred to as B sub G or B sub H. So let's drop a quick example. Let's assume for a second here that we have three inequalities. So I'm going to call it H1 of X, H2 of X, and H3 of X. Now I'm just doing this because I want to show how the sizes relate to one another. All right, so we know that H of X is equal to A sub H times X minus B sub H is less than or equal to 0. So what will A sub H look like? Now let's assume for this example we only have two primal variables. So what that means is we need this matrix to spit out something with a height of 3, and we need it to accept something with a height of 2. All right? And so if we look at the sizes here, we can see, right, that our X array will have a height of 2, and the output should have a height of 3. And so we need, in order for these dimensions to agree, we need for this matrix A sub H to be a 3 by 2 matrix. All right, and I'm just going to put X's, or I'll put little H's here to represent those elements because we really don't care about what they are numerically. So then we multiply this by X1 and X2, right? And then we subtract out our B sub H, and that should also have 3 elements. So you can see here, if we have 3 inequality constraints, we should have an AH matrix which has a size of 3 by 2. We should have an X, well, we're assuming that our X array has a size of 2, okay? And our B sub H should have a size of 3, or a height of 3. Now, I could use the term contravariant and covariant rank here, however, I'm not going to dive into that. And so now we can see what this matrix would look like if we had 3 inequality constraints as well as 2 primal variables. Now, what would this look like? The objective function, right? We know that the objective function is simply the product of C and X, so they should have the same length or same width and height respectively. So if we have 2 decision variables, okay, that means we would have something that looks like this as our objective function, right? Because our objective function should always be spitting out a single scalar value. All right, so now that we understand the form of these equations, let's try to convert what we had back here into the quote-unquote standard form. So we're going to convert this linear programming problem to the standard form. The standard form employs several assumptions for consistency. Again, I'm not making these up. These are commonly accepted assumptions about the form of these problems, hence, right, the name standard form. Okay, first is maximization. So generally, we don't represent these types of constraint optimization problems or linear programming problems in terms of minimization, which goes against what we had talked about for quite a while. But the standard form asks that we define it as a maximization. And that's pretty easy to change, right? We can take any minimization problem and convert it into a maximization problem by simply multiplying the coefficients by -1. So you go back here, you can see I was pretty specific about using the coefficient C sub min, right? Because this is a minimization problem, that would be equal to the coefficients we would use for maximization. So converting between minimization and maximization is really not that hard. For this module, when we simply write C, we're assuming that that would be the set of coefficients appropriate for the maximization problem. Okay, so we can always convert the minimization problem to maximization. The next is inequalities, or the presence of inequalities versus equalities. So generally in the standard form, we only have less than or equal to inequality constraints. We don't have any equality constraints. However, that's a problem that's pretty easy to solve because we can take any equality constraint and convert it into two inequality constraints, right? If we have something like g of x equals 0, right, that's the same as saying we have one h of x that is less than or equal to 0 and one negative h of x that is greater than or equal to 0, right? Because there's only one value of x that can satisfy both of these, and that would be when x is equal to 0. All right, so what we're going to do is turn our g of x into two constraints, right? We have h of x is less than or equal to 0 and negative h of x is less than or equal to 0. Because again, in the standard form, we are assuming that they are all less than or equal to inequality. So we can't use greater than. And then lastly, the primal variables. For the standard form, we generally assume that the primal variables are greater than or equal to 0, which doesn't necessarily fit with all the problems we look at, but this is part of the standard form. Again, please note the references up here in the right-hand corner. I encourage you to check those out. So here we have the standard form of the linear programming problem. We have an objective function, which is defined as the coefficient of a coefficient array, or the product of a coefficient array and x. Again, we're assuming that this is the maximization array, and it's just transposed because if we originally assumed it was a column, we have to transpose it to make it an array, so the inner product works out. Okay, now you can see the equality constraints, they are now gone, right, because we no longer have those. They've been rolled into the inequality constraints, so there could be a case where the number of inequality constraints increases as we go from the non-standard to the standard form. And we assume that all of our primal variables are greater than or equal to 0, and we have to assume, as always, that our dual variables are also greater than or equal to 0. And this is nothing new for this linear programming problem. It's something that's left over from all the other instances where we dealt with constraint optimization problems with inequality constraints. So we want to solve this problem, or we want to convert it to its dual form. The nice thing about this linear constraint optimization problem is there's a general dual form that we can present that we can always use without having to rederive it every time. So let's try to get to that point. The first thing that we need to do is to define our Lagrange function. Nothing new here. Again, our Lagrange function is equal to the sum of our objective function plus lambda times g of x times mu times h of x. Okay, minus mu times h of x. So a couple things to clarify. Well, first off, this is no longer considered, right, because we've assumed that in our standard form, we got rid of our equality constraints and converted those to inequality constraints. Next, why is this a minus right here? Previously it was plus, right? This goes back to the difference between a minimization and a maximization problem. I think we hinted at this earlier. So if we assume that mu is greater than or equal to 0, we haven't changed that dual feasibility condition, then a negative sign is required here to ensure that h of x greater than 0, that's a penalty, is negative and works against our objective as described by maximization. To make a long story short, for the minimization problem, this was plus, and for the maximization problem, this will be equal to minus. Now you can see here that what I did was I split mu into two different parts because we have an inequality constraint that says that negative x must be less than or equal to 0, which is also technically part of h of x, but I parsed these out. So now we have the Lagrange multipliers for the quote-unquote actual h's, actual inequality constraints, and then we have the Lagrange multipliers for these primal variable constraints right here. Okay, so we move on now to an alternate form. This is really kind of just simplifying. You can see going from here to here, what I did was I split out these two terms, the product of mu sub h and h, and mu sub x and x. So now instead of one term, we have two terms, and this still disappears. So we have this term, we have this term, and we have this term. 1, 2, and 3. 1, 2, and 3. And then we can put this into our linear form. Going from here to here, what we did was we substituted in ctx for f of x, and we also substituted in a sub h x minus b sub h in for h of x. So we really did a substitution going from the alternate form to the linear form, and now we can see that this final linear form of our Lagrange function is equal to our objective function ct times x minus mu sub h, which is part of our inequality Lagrange multiplier, times h of x which is a sub h times x minus b sub h. And so we end up with plus mu sub x times x. Now, you may be a little bit confused by the jump from here to here, and the reason for that is because this is actually erroneous. This is not a plus, this should be a minus, right? Because this minus should carry over here to mu sub x, and so we have minus mu sub x times negative x, which gives us a positive right here. So the third line was correct, and the second one had a mistake in it. But anyway, the main point is that this third line, the linear form of the Lagrange function, is correct. Okay, so we're following the general steps that we've used in previous optimization problems, right? When we applied the duality principle previously, our first step was to minimize the Lagrange function with respect to x, but that was the case where we had a minimization problem. Now we have a maximization problem, so we flip everything. So the next step is to maximize our Lagrange function with respect to x. Now I'm kind of retreading that same question, asking similar questions here. So isn't the dual Lagrange function defined as the minimum with respect to x of the original Lagrange function? Shouldn't the next step be to minimize the Lagrange function with respect to x? And I kind of already answered that. No, because the standard form asks us to maximize our objective function f, and so all the other minimizations and maximizations are flipped. So consequently, duality as applied to maximization problems provides an upper bound on our optimal output of the objective function, not a lower bound. And the dual Lagrange function, one thing that doesn't change is that this should still be in terms of the dual variables only. Now in this case, we no longer have lambda, so it should be in terms of mu only. All of our x's should have disappeared by that point. All right, so let's try to perform that maximization. This is step number 2. 2a is to differentiate the Lagrange function and set this gradient equal to 0, right? This is a similar process to what we've used in many other previous problems and modules. So we take the derivative of the Lagrange function with respect to x, and if we go back here, right, we see that this term right here will simply yield us ct, right, because the x goes away. This term right here will yield minus mu h transpose times ah, the x goes away. And then we're also left with plus mu sub x, and the b of h no longer carries over. So we have ct minus mu sub h, a sub h plus ux. All right, and that's what we have here, ct minus mu sub h, a sub h plus mu sub x, and that's equal to 0. Now there's different ways we solve these types of gradients each time. In this case, we're not putting in terms of x, right? Our x has gone away, it's disappeared from this gradient. However, we can set up a new constraint which reflects that relationship. So we're going to solve for c. We're going to solve for this value right here, push everything else to the other side, and what we end up with is c transpose is equal to mu sub h times a sub h minus mu sub x, right? Just taking this whole term right here and pushing it over to the other side. Or if we wanted to get rid of the transpose, right, we end up with this right here. Now note that when we transpose these two components, right, their orders will switch, they'll flip, right? This is a law of applying a transpose to a product of two algebraic objects. So we end up with a constraint that says that to satisfy this stationarity condition of KKT, that C must be equal to, well, everything that's written right here. I don't think I have to repeat it again. Okay, so now let's define our dual Lagrange function. Okay, we've done this several times in other examples. Many times what we would do was try to insert some sort of a new x value. We don't really have an x value in this case. However, we do have a new constraint. So what we can do is we can substitute in every time we see a c or a c of t, c transpose, right? We can substitute in this new value shown in blue, and I'm simply just taking that from right here, right? C transpose is equal to mu sub h, a sub h minus mu sub x. Mu sub h, a sub h minus mu sub x. So what we're doing is, instead of substituting in a new x value, we're substituting in this constraint. Now going from here to here and then here to here, really all we're doing is simplifying this equation. And so you can see we multiply the product of these two together, product of these two together, we separate out b sub h. Anyway, I'm not going to go into all the algebra. If you're interested, you can take a look yourself. But what we end up with is two terms, right? This term and this term, which cancel one another out. Okay, and we're left with only the final part of this equation, which is mu sub h transpose times b sub h. And this is our dual Lagrange function. So from steps 1 through 3, there's two important observations we can make, okay? And they allow us to reformulate this optimization as shown on the next slide. The first, I'm going to start from the bottom and go up. The first is we have this new constraint which defines what our x max L was. Right? This constraint must hold in order to apply the stationarity constraint or condition of KKT. We know that C must be equal to A sub H transpose times mu sub H minus mu sub X. So this is a new constraint. We also have a new equation for minimization, okay, which is our dual Lagrange function in terms of lambda and mu only, although we don't really have a lambda, so we can get rid of that. And so what we end up with is mu sub H transpose times B sub H, where all this is coming from, right, our H of X constraints. Why is this minimization and not maximization? Right, because we always apply the opposite to the dual Lagrange function as compared to what we apply to the primal. So in this case, it's a maximization problem. We were applying maximization in the first step of duality, and now we're applying minimization. Let's take a look at our linear programming problem in its new dual form. So first, let's focus on the dual objective. Okay, the dual objective is going to be to minimize our dual Lagrange function with respect to the dual variables lambda and mu, although we don't have any lambda, so we can get rid of that, with the assumption that mu is greater than or equal to 0. And this dual Lagrange function is exactly what we derived from 1 or 2 slides back, right? It's mu sub h times bh. Now, duality tells us, and I should flip the sign here because actually now it's greater than or equal to, that this dual problem gives us an f value, an optimality, that's an upper bound on the true value, meaning that it's greater than or equal to f of x sub OPT. It's greater than or equal to the true optimal value. However, I really don't need this inequality here because for this linear programming problem, we know that strong duality applies. And so the solution yielded by the dual and the primal optimizations for this linear programming problem only, they're equal to one another. And so our duality gap equals 0. Now let's try to derive our constraint in the form that we want it. Up here we have our original constraint where we saw that C minus A sub H transpose times mu sub H plus mu sub X is equal to 0. What I did was then take this term and move it over to the other side of the equation. All right, and so we end up with C minus A mu is equal to a value that's less than or equal to 0. And so what we do here, which may seem a little bit funny, is we actually get rid of this and we replace the equality with a less than or equal to 0. This is essentially the same as saying it's equal to negative mu sub x, but we're not going to consider that moving forward. And that's fine because we're replacing the equality with the inequality. And then going from here to here, we simply just flip the signs, okay, and move C over to the other side of the equation. What we end up with is the final form here of this constraint. A sub H transpose times mu sub H must be greater than or equal to C with the mu sub X. Well, where did that go, right? That was cooked into the inequality operator right there. So the main two pieces of this are going to be our dual objective function as well as the new final form or updated form of the inequality constraint. All right, and so that's what we have shown right here. If we reformulate our primal linear programming problem to a dual linear programming problem, we end up with what's shown here. Now, previously, right, I don't want to take up too much space, but previously our goal was to maximize our objective function subject to a constraint h of x is less than or equal to 0. Okay, and so this is our primal form of the problem, and our objective there was to solve for the optimal primal decision variable. Now, we've redefined it as a dual linear programming problem. Now our objective function, instead of being maximization, it's in terms of minimization. So we want to minimize the dual Lagrange function in terms of mu, and it's defined as shown here. And it's subject to two constraints. The first being A sub H transpose times mu sub H is greater than or equal to C. And then we can't forget about our dual feasibility condition, which says that all the mu values must be greater than or equal to 0. And this is just a more compact form of what's shown above. So I want to be clear here what we're doing in this module, right? In modules 4 and 5, we already talked about what duality is, the role of duality, how to apply it to these general types of problems. In this module, what we're doing is something very specific. We have a very specific type of linear programming problem defined in this standard form. We're applying duality to it. Fortunately, strong duality applies, so we know that the dual problem provides us the same solution as the primal problem. That's nice. And what we're going to do is define what we've already done, really, is define this revised form. So if we can't solve the primal optimization as it was defined previously, we have an alternative in trying to solve the dual formulation. And so this slide summarizes what we just talked about. It compares the primal and the dual forms of the optimization problem. Okay, on the left-hand side, we have the primal form. We're assuming that we're only maximizing. So we want to maximize an objective function with respect to x that's defined as C transpose times x. Okay, and here we can see the C transposed as a row-oriented array and x as a column-oriented array. Now, when we go to the right-hand side, we see that our dual objective function is different, right? We're minimizing with respect to mu. Over here, we're optimizing with respect to the primal decision variable. Over here, we're optimizing with respect to the dual variable. And so this is equal to, and this is our dual Lagrange function, is equal to B sub h transpose times mu. On the left-hand side, we have constraints. Essentially, right, what it says is A sub h of x must be less than or equal to B sub h. And that's the same as what we had previously where we wrote A sub h of x minus B sub h is less than or equal to 0, right? So these two are equivalent. And so, right, again, A sub h, that's this matrix, then we have our primal decision array, and then we have B sub h. And this also mimics the form that I hand drew when I was showing the sizes of these matrices. Now when we go over to the right-hand side, our constraint is different. We have A sub h transposed times the column-oriented array of the dual variables must be greater than or equal to what originally, right, was the coefficient of the objective function. Why is this transpose important? Right, because the height of x and the height of mu are different. And so in order for the dimensions to agree for the matrix algebra, right, they need to be transposed. But we also showed why this was needed theoretically in our derivation previously. And still, we're sticking with the dual feasibility condition that mu must be greater than or equal to 0, whereas previously it was x must be greater than or equal to 0. So hopefully this slide provides a really concise and relatively easy to understand comparison of the primal and the dual optimization problems that may be applied to dual linear programming problems in that standard form. Okay, so let's talk about lambda and mu. Really, we're just talking about mu and its significance and what it means. I know we've discussed this a little bit so far, but I want to dive more into it because I think either the next module or the one after that, the final one in this series, discusses these values at length. So let's introduce the term of a shadow price, and that's one interpretation of what these dual variables represent. A shadow price represents a change in the optimal output, right? Remember that f of x optimal is the most optimal output, the most optimal condition that we can achieve. So represents the change in the optimal output observed when a constraint k is strengthened or relaxed by 1 unit. And right, we're only dealing with h of x inequality constraints, so we don't have to consider g of x. Okay, so when we talk about strengthening a less than or equal to inequality constraint, what we're doing is talking about reducing its maximum value, right? Because that value represents the area or the range within which the system may feasibly exist. And so if we reduce that upper bound, right, we're tightening those constraints. And we relax the less than or equal to constraint by increasing its maximum value. Now, the shadow price represents marginal utility or cost, okay, of strengthening or relaxing a constraint k. As we said 1 or 2 modules back, right, it represents the relationship between optimality and that inequality constraint. It represents the optimal unit price of scarce resources for market equilibrium. Now, this is a really interesting statement, and it's one we're going to talk about at length in that final module. So if you're interested in this statement, keep an eye out for that. So we will observe that the cost of purchasing a resource equals the estimated additional income, or at least that should be the case when we're at our optimal state, when we achieve the market equilibrium. I'm going to leave that there because we have a whole module to discuss that at length. And so the term shadow price is often used for economic related optimization problems. And again, not to be repetitive, but we're going to talk about that in the final module. So let's dive into shadow pricing a little bit deeper, and let's take a look at 2 different cases. So I'll call this case A and case B. Okay, in the first case, we have an optimal solution which represents that optimal primal x solution when a kth limit is at its original value. So what is that going to look like? Essentially, it'll look something like this. We have A of h times x minus B of h should be less than or equal to 0. So that's the first case. The second case represents the solution when that limit is reduced by 1. Okay, now this actually, when we talk about reduced by 1, it's on the other side of the inequality. So I'm actually going to write that as A sub hx minus b sub h minus 1, which ends up being a plus 1, is less than or equal to 0. So here is our original offset or original constant value in our inequality constraint, and here's what it looks like when the limit is reduced or strengthened by a value of 1. And we can take a look at this in a little bit more detail. Let's move this over to the other side. And so what we end up with is a sub hx is less than or equal to bh minus 1, so we can see it's being tightened. Okay, so the equation below demonstrates that shadow prices represent the marginal cost of a resource associated with strengthening, or in other cases relaxing, but we're looking at strengthening, a given constraint. For example, it could be the effect of distortionary market forces like tariffs. So what is this complicated looking equation down here at the bottom? Let's just concentrate on mu for a second. Okay, it says that the shadow price is equal to the delta F, or how much the optimality of the system, the output of the objective function, changes, right? Because up here we have the first case, which uses the first inequality constraint. Here we have the second case, which uses the updated or tightened inequality constraint, and that yields the numerator, which is delta F. So how much does the optimality change? Could go up, could go down. Generally goes down. Okay, and we divide that by the change in our b sub h, which we're just calling b right here. Okay, so we have b minus 1, right? That's the same value here and here. Now, obviously, these are going to go away, so we're left with a 1 as our delta V. So we expect the optimality to decrease if the constraint is tightened, like I said a second ago. And so this gives us a little bit of a preview of what the shadow price represents with respect to constraint optimization problems in general, as well as those that are economic focused. And so, like many modules, I want to end this with a short summary as well as some clarifications. So the objective of this module was to define a transform that redefines our primal linear programming problem in terms of its dual or dual representation. It redefines the primal linear programming problem as a dual linear programming problem. It builds upon the standard form that we looked at in the beginning of this module. So the standard form of the linear programming problem statement. And we also define many of its components, including a sub h, b sub h, and c, which represent the coefficients of the objective function in its linear form. Now, one thing that I didn't write explicitly on here, but is very important, is that strong duality applies to this linear programming problem, which means that the solution that the dual form yields should be equal to that which the primal form yields. It doesn't provide simply a bound. Now, the last slide that we just looked at is a really important one. It provides a summary of this transform between the linear and the dual form that's independent of its derivation. So you don't really have to understand most of this module, all that derivation, in order to understand the last slide and comprehend how to transform the primal form of the linear programming problem to its dual form. Now, I did want to ask this question one more time. Why are we bothering to talk about primal versus dual forms? And this is a topic that we addressed, I think, in module 2 or number 3. So I'm not going to reiterate the reasons. It's really the same reasons we discussed previously. Now, to give a little bit of a preview of the last module, when we start to talk about the economic interpretation of these problems in more depth, I think that module provides some nice explanation, a more practical explanation of why this process is important. And then lastly, I did want to point out there was unfortunately one error in this module where I accidentally, I think it was maybe the 5th, 6th, 7th slide, I accidentally said that for this module we define the dual Lagrange function as the minimum of the primal Lagrange function, when, as we said several times throughout this module, it's a result of maximizing that primal Lagrange function with respect to x. So there's 2 modules left in this series on constraint optimization. The next discusses a pretty specific example. So we're going to look at a factory. We're trying to produce some product. There's a market price, or there's a price at which we can sell this product. And we also have constraints on how much energy we can use, how much manpower, etc. So it'll be a good opportunity for us to implement some of the lessons that we learned from this module. So we're going to be taking a linear programming problem that is practical, again, based on this fictional factory, and solve it using, I think, both the primal and the dual forms. The last module, which I think I've hinted at before, is especially interesting because that's where we're going to dive into the economic interpretation of these types of problems and discuss more the significance of shadow prices and how they can be a really powerful tool for many engineering and STEM related problems.